Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 2.4 titled Writing Direct Proofs. Alright, so we're getting into the heart of Chapter 2 where we start going over different proofwriting methods, proofwriting techniques, and this is the simplest of them. Just a direct proof where you start with a hypothesis and then write, steps, true statements that follow and their reasons, and you end with the conclusion of a statement. All right. So, again, a lot of reading in these, unfortunately. I'll do my best to, give you the main points. So the form of a direct proof, right? A statement that you're gonna you usually write a direct proof for a conditional statement, if-then statement. Not always, as we'll see in later sections, but a lot of conditional statements will involve, to prove them, will involve the use of direct proof. So many mathematical theorems take the form of a conditional statement, right, in which a conclusion follows from a set of hypotheses. Theorems of this kind can be expressed as, P implies C, and you've seen this symbolism before, right? If P, then C, where P is a proposition which asserts that a set of hypotheses are true, and C is the conclusion. Sometimes P is simply referred to as the hypothesis. In a direct proof of a conditional statement, an if-then statement, the hypothesis P is assumed to be true, and the conclusion C is proven as a direct result of the assumption. So you start with the hypothesis, you start with whatever statement P is, and you end with C, right? You try to show that C is true. Many theorems are conditional statements that also have a universal quantifier, such as, for every integer n, if n is odd, then n squared is odd. So you see there's a universal quantifier there for every. The domain is all the integers, right? And then you have your conditional statement with the hypothesis n is odd, and the conclusion n squared is odd. Right, so I would start with the statement, n is odd, and end with the statement n squared is odd in a direct proof. So you have a domain, right? And every statement has a domain involved, right? What the statement is about, right? This is a statement about integers. So the domain of variable n here is a set of all integers. And then you have, remember, predicates from chapter 1. D of n is the predicate that says n is odd. Then the statement is equivalent to the logical expression, for all n, for every integer n, if n is odd, then n squared is odd. Right? D of n implies d of n squared. And you can do this also. You can, if you want to, you could take a statement in English and write it in logic, right? Write it with our logical symbols, and you can do that if you wish as well to if it makes it clearer for you. So a direct proof of this theorem would start with n, an arbitrary integer, right? Remember to prove a universal statement, this is about every integer. You would start with an arbitrary integer, have a variable represent any integer, right? Not just a specific one. Assume that n is odd, right? Assume the hypothesis, and then prove that n squared is odd, right? And end with the conclusion. Frequently, now the way it's worded here, just please know that a conditional statement can be worded in many different ways. You saw that in chapter 1, right? Your statements involving if-then can be expressed in many different ways. So this statement up here is equivalent to all these other blue statements. if n is odd, then n squared is odd, an odd integer, right? They mention the word integer here, so they're saying, for every integer. Or they're at least pointing out that the domain is the integers because the word integer shows up. The square of every odd integer is also odd. Same thing. Let n be an integer that is odd. We will show that n squared is also odd. This is like the way we would start the proof. Right? Remember, you introduce your variables and show what's being assumed, right? And then you state what's going to be proved for the reader, right? Make it easy for the reader to read. All right. So here, the first activity, we're asked to match each theorem statement with the correct set of assumptions in a direct proof. If I was looking at this statement and trying to prove it, what would I first assume? The average of two real numbers is greater than or equal to at least one of those numbers. So the statement's about real numbers, and basically, again, a lot of these statements you can rewrite as an if-then statement, a conditional statement. This is saying, if I have two real numbers, then the average of those numbers will be greater than or equal to at least one of them. So I'm only starting here with two real numbers. So I would simply be assuming here, I'd simply start off with the assumption that x and y are real numbers, right? That's it. This next statement, the difference between two distinct real numbers is not equal to 0. So I'm starting here with two real numbers that are distinct. That's two real numbers that are not equal. And then trying to show that the difference between them is not 0. So I would start off with, I would be assuming here that x and y are real, but not equal. Right? They are distinct. And then, the product of two positive real numbers is a positive. So again, here this is a statement about two positive real numbers. So that's what I'd be starting with, and then showing that their product is also positive. So the only thing I'd be starting here is x and y are real, and they're both positive. Right? I'll start with two positive real numbers in a proof of that statement. Now these are not proofs. This is just the beginning of the proofs. Right? All right, so writing direct proofs, the actual title of the section. Now I'll actually go to a piece of paper and show you how I would write the proof to this statement here. All right, so we're given a theorem. The square of every odd integer is also odd. All right, this is the statement earlier. The square of every odd integer is also odd. So you could rewrite it as an if-then statement. So I'm going to do that on a piece of paper and show you how I would go about proving it. Okay, so I've written out the statement. Now the statement they gave us was the square of every odd integer is also odd. Another way of saying this is if n is an any odd integer, right? Because this is saying the square of every odd integer. If n is any odd integer, then n squared will also be, right, is an odd integer as well. Right? Hopefully it makes sense. And again, for a lot of statements, not every statement, but for a lot of theorems, a lot of statements, you will be able to write it as an if-then statement. Okay, so before I get into the proof, I'm going to identify my hypothesis, right? That's the if part, right? This is called the, remember the and we've seen this in chapter 1 on logic. Right, this is called the hypothesis, right? Then the then part, n squared is an odd integer. This is the conclusion, right? And in a direct proof, and this is a kind of a side note here. In a direct proof of a conditional statement like this, you start with you assume the hypothesis is true. You assume the hypothesis is true. and then you go through, you write your steps and the reasons for those steps, and you end, with the conclusion. You show the conclusion is true. Okay, so this is the structure of a direct proof of an if-then statement or a conditional statement. All right. So I wrote the theorem. Now comes the proof, right? So if you recall, I want to start off, I'll write the word proof to indicate to the reader that the proof is beginning. And then usually we start off with our assumptions. All right, what are we assuming? So I'll say let n be an odd integer. All right, this is my assumption. I'm assuming n is an odd integer, and I'm introducing n as well, right? Every time there's a new letter or a letter you introduce to the proof, state what it is. Right? Introduce it to the reader. Let n be an odd integer. And that's the only assumption here, right? That is the hypothesis. N is an odd integer. Now, very often in a proof, as you saw in previous sections, we'll also state for the reader what we're trying to show, what this proof is going to lead to. So I state the hypothesis, that assumption, introduce the variable n, then I will say after, we will show, right? And usually we use the word we, not I. Okay, I don't know why that is, but just make it more general. I don't know, but I'll say we will show that, the conclusion. We will show that n squared is an odd integer, right? Or that or show that its square is also odd. But I'm just going to write the conclusion. We will show that n squared is an odd integer. Okay, so now I start with this assumption that n is odd, right? I start with the hypothesis, and then go from there, and I eventually want to show that n squared is odd. In other words, now something else I could do here is write another way to say this. I could also say, now this is optional, but I could say, in other words, we will show, and this is optional, right? I don't have to write this, but I'm going to. What does it mean for n squared? What would it mean for n squared to be odd? And this is where definitions come into play, right? I bring definitions into the proof. In other words, we will show that n squared is equal to, say, 2 times m plus 1 for some integer m. And again, I'm introducing m here for some integer m, and I'm telling you what m is. M is an integer. Okay. Yeah. Now this like I said, this in other words, this isn't proving anything. I'm just saying this statement again. Right? I'm saying this statement again, but just in another way. What would it mean for n squared to be odd? That means that we're trying to show that n squared equals 2 times m plus 1 for some integer m. Right. Okay, so I'll skip this. I'll start a new line. So again, I'm starting with the assumption of the hypothesis. We're assuming that n is an odd integer. Now again, I'll bring in the definition. What does it mean to be odd, right? So by definition, right? By definition, n must be equal to, say, 2 times k plus 1 for some integer called k. Right? Again, every time a new letter comes in, I introduce it. I let the reader know what it represents for some integer k. And I want to use this to basically see if we can rewrite n squared as 2 times some integer plus 1. So I can do that by plugging in this expression to n squared. Again, I'm not using this equation. Right? I'm not using this equation, because if I use this equation, that is circular reasoning. That's using what we're trying to prove. I'm trying to start here and eventually get to this. Right? So I'll write that here. I'll write that. Don't use this. Right? Don't use this in the proof. Okay, you have to end with this. All right, so I'll say plugging n equals 2k plus 1 into n, just say n squared, right? Now, so I have what n is odd. Let's look at the expression let's look at n squared, right? Because the conclusion is about n squared. This yields or gives the following. All right, and then comes some like little algebraic statements. All right, so I put a colon, and then I'm going to have some block of equations. Yields n squared equals, and again I'm replacing n with the quantity 2k plus 1. Right. So n squared would be the quantity 2k plus 1 squared, and now comes some algebra steps. I don't have to really justify the algebra steps as long as they're valid, and I don't go more than one step at a time. So this is squaring the 2k plus 1. What's 2k plus 1 times 2k plus 1? That would be 4k squared plus 4k, remember foiling, plus 1. All right? And then I'm almost there, right? Again, I'm trying to express n squared in this way, as 2 times an integer plus 1. Well, you got the plus 1 here, so now I'm going to try to express this first two terms as 2 times an integer. See that they both have a factor of 4, so they both have a factor of 2 at least. I'll pull a 2 out, and then I have 2 times, and then 2 times k squared plus 2k. And then plus 1, right? And that's just from factoring. All right, I'm going to stop it there. All right, I'm going to stop it there, and then we'll make a statement here about 2k squared plus 2k. I'm going to say 2k squared plus 2k is this integer m that I introduced earlier. All right, and I'll make the statement, since k is an integer, right? We've already introduced k as an integer earlier, right here. Since k is an integer, this 2k squared plus 2k is also an integer, right? Remember that was part of the from the best practices section 2.3. We can assume integers, the set of integers is closed under addition and multiplication. So if k is an integer, k times k would be an integer, times another integer is an integer, plus another integer is an integer. So this 2k squared plus k is also an integer. And let's say it's that integer m, right, that I had up here. Let's say m, right, is also an integer, say the integer m. Therefore, n squared is equal to 2 times m. Right? I'm replacing this 2k squared plus 2k times with the integer m plus 1 for an integer m. Right? By definition, n squared is odd. Right, by definition here, by the definition of what it means to be odd, by definition, n squared is an odd integer, and that is exactly what the conclusion was right? That's what I said we were trying to show, right? Up here, we will show that n squared is odd. I started with the hypothesis that n is odd, and then through some algebra here, through some and the assumption that the integers are closed under multiplication and addition, we have shown finally the conclusion: n squared is a non-integer. And then I end the proof with a filled-in little box here. And you can use that, or you could use that symbol QED, which I mentioned earlier, the Latin quod erat demonstratum, which is what we're trying to prove or what we're trying to demonstrate. There, I have proven directly the statement: the square of every odd integer is also odd. Right, so I know that when you first see when you first see proofs written out in full sentences, it can be a bit tedious, right? A bit confusing, because you're not used to doing stuff like this, especially if you've never taken a proof writing before or discrete before. It can be a bit cumbersome, a bit unwieldy, but you'll get the hang of it. Right? Remember section 2.3 went over all those best practices. I state the theorem. I indicate when the proof is starting. Make assumptions, right? List my assumptions. Introduce variables. This was optional. The telling the reader what you're going to show, that's optional. And then full sentences starting with the assumption, and then again full sentences into some algebra here, and then eventually leading down, after making statements and justifying statements, showing the conclusion, and then indicating when the proof is ending. Okay, so going back to the page, right, they go through that in this animation, right? Now they don't do the "we will show n squared is an odd integer," but they eventually do the same thing here and show what I did. Right. So again, you can play the animation, go one step at a time, and they in the red lettering, they're saying why they're doing things. Why am I writing this in this proof? All right. Okay. All right. Next activity is another like fill in the blank. So I'll read it through. Right, below are the steps of a direct proof for the following theorem. And in fact, I'll do it on paper, and then you could fill in your own. Right. The difference between two even integers is even. And I'll also write this as an if-then statement, right? A conditional statement, and go into the proof. Okay, so here we have it. All right, I've written the theorem that was stated, right? The statement is: the difference between two even integers is even. Now, again, you can introduce your own letters if you want. I used x and y, but this is a statement about two even integers, right? I'd be starting with two even integers and then trying to show that their difference is also even. So I wrote this as an if-then statement this way. If x and y are, two even integers, right? If x and y are even integers, then their difference, right, then x minus y, is also an even integer, right? Okay. So again, I would get in the habit of trying to practice that, trying to rewrite statements in an equivalent way as a conditional statement. Now, you're not going to always be able to do it, all right? But a lot of these theorems, a lot of these statements that we're going to see in this chapter, you should be able to rewrite as a pretty good if-then statement. All right, so as before, I'll identify what I'm going to start with. Right, here's the hypothesis, right, the if statement. So I'm going to start with the assumption that I have two even integers, right? X and y are even. And the then statement, right, this here after the then, x minus y, their difference is an even integer. That's what I'm going to end with, right? The conclusion. Okay. All right, so I start the proof. I'll indicate that the proof is beginning. And I'm going to say, let's let's let x and y, again, I'm going to introduce some variables, introduce these, tell the reader what they are. And from the hypothesis here, start with the hypothesis. I'm going to say let x and y be even integers. All right, then the optional part. All right, you don't have to do this. I personally would enjoy doing this. I like doing this to let the reader know where this is going. Then I'll say we will show. Right, we will show that their difference, right, their difference, x minus y, is also even. Okay. Now again, you could do the in other words, say what that means, but I'm not going to do that this time. Right? You can do that like I did in the last one. You can say, in other words, we're going to show that x minus y is equal to 2 times, m, where m is an integer, right? What does it mean to be even? But I'm not going to write that this time. Right? So I start with an assumption. I write out my assumptions and introduce new variables, tell you what they are. X and y are even integers, right? Starting with what the hypothesis is saying. This is just a for the reader, right? Show the reader, tell the reader where this is going to go. All right, so then starting with the assumption, x and y are even integers. So again, what does that mean? We have to use some definitions here. So by definition, right, by the definition of even, x must be equal to 2 times, say, k, and use whatever letter you want as long as it hasn't been used already. This is that existential instantiation you saw in section 2.3. By definition, x equals 2k for some integer k, and right, we've also stated that y is an even integer, right? And to complete the sentence, y must be equal to, say, 2j. Again, a different integer, because if you use k again, that would mean that x and y are equal. But we're not assuming that x and y are equal, right? These could be the same. They could be the same even integer, but they could also be different. So I'm using j instead, a new letter. And I'm introducing it, right? I'm telling the audience, I'm telling the reader what j is, right, for some integer j. Okay. End of sentence. Now, I start out with the hypothesis. Now I'm trying to show that x minus y is even. So I want to eventually get into the expression x minus y. Right, well, to do that, I'm going to plug these expressions into the expression x minus y and see where that takes us. See if that helps me show that x minus y is also even. So like the last proof, I'm going to say plugging x equals 2k and y equals 2j into the expression x minus y yields the following. Right, I'll start off some algebraic lines here. Yields the following: x minus y would then be equal to, I'm replacing x with 2k minus, and I'm replacing y with 2j. And if you recall, right, what does it mean? We're trying to show, always keep in mind what you're trying to show. We're trying to show that x minus y is even. And you have to remember what it means to be even. Being even is being a multiple of 2. So can I rewrite this as 2 times an integer? Well, if you look at these, both of these terms have a factor of 2 in it. I can factor that out. If I pull a 2 out, this will be 2 times the quantity k minus j. All right, and then we have to figure out, is this k minus j also an integer? And yes, right, we have stated earlier that k is an integer and j is an integer, And by our assumptions, from the previous section, the certain assumptions you can make without proving. Remember, the integers are closed under subtraction, meaning when I subtract two integers, I get another integer. So underneath this, I'm going to say, hey, since k is an integer, or I'll just say, since k and j are integers, since k and j are integers, k minus j is also an integer. And I can call it something, right? Let's say is also an integer. Let's say m again, right? Again, just a new letter that I haven't used. Right? Therefore, or then, I guess, therefore, x minus y is equal to 2 times m for an integer m. Right, we know that m is this k minus j. M is an integer. This is the definition of oddness, or I'm sorry, evenness. It's a multiple of 2. So then by definition, x minus y, by the definition of evenness, right, by definition, or therefore, I guess you could say, or thus, or hence, some fancy words, x minus y is an even integer, right, because it is an integer multiple of 2. And this is exactly what we were trying to show, right? That was the conclusion, right? So I started with my hypothesis assumption, and I've ended with the conclusion, shown that the conclusion is true. So if x and y are even, x minus y is also even. I am now done with the proof. I have shown what I'm trying to show. And fill in this little black box here, or write QED. Sometimes it's not even a filled in box. Sometimes it's just an open box, but some sort of symbol to indicate the end of the proof. There. That was another example of a direct proof of some conditional statement, some if-then statement. Okay, so back to the page. Again, you can fill in the. Now they might not have used the same letters that I did or the same words, but the steps are probably very similar. All right, so you can fill in the steps on your own. All right, now I've mentioned the process of writing proofs. Now so far in my proof writing, I just wrote the proof, showing you this last one. All right, I'll show you this last one again. I just went right into it. I just said, hey, here's this theorem, and I just went proof, and I just started writing the proof. That does not happen very often. The proof is like the final draft. All right, the proof is the final draft. Very often, I got to do some rough work. So here, the proof. Right, the proof you write is the final draft of your work. If you remember writing like a term paper or an essay, the proof that you actually produce, the proof that you write, is when you're done putting together. Again, I wrote the proof. The last 2 proofs, I just wrote them without thinking about how to put them together because I've done them a bunch. All right. But with less experience, you're probably going to have to do more and more preliminary work, rough drafts, and then the proof is when you organize all that work and put it together. So very often, you must do some preliminary work, some work before you actually put together a finalized proof. So like you do some brainstorming, some exploring, some scratch work, some explorations, so some scratch work. You do a bunch of stuff before, and then you organize your thoughts into a proof. You organize your thoughts into a proof. And that's what you eventually show me. All right. Don't show the reader this. Right. Do not show the reader. Right. This stuff is not shown to the reader. Okay. The reader doesn't want to see that. Now, sometimes, if the reader's curious, they'll ask whoever wrote the proof, how did you do this? How did you structure this? How did you figure this out? And then perhaps the author of the proof will show or reveal the work behind the proof, the behind the scenes stuff. Right? This is all behind the scenes. The reader gets the organized version. The reader gets the final draft. Hopefully this is making sense. So let me show you. Now they go through an example here. All right. Here's a theorem. And you see scratch, they have a video here even. You can watch it in here or watch it or pull it up on YouTube. Here's a theorem. If x and y are positive real numbers, then x divided by y plus y divided by x will be greater than or equal to 2. And this is for any positive real numbers, x and y. All right, so they go through this video, brainstorming, a direct proof, scratch work. This is the behind the scenes stuff, putting it together before you organize it. All right, doing some preliminary work before you actually organize it, and then they have the proof beneath it. Here's the final draft. So let me show you what I'm talking about. All right, I'm going to do this theorem. All right, and I'll show you, the preliminary work, the brainstorming, the exploring, the scratch work that is done before I organize it into a valid final proof. Okay, so here's the theorem. And again, what I'm about to do is not the proof. Okay, the reader of the proof will not see this work. Here's preliminary work. This is before, because a lot of times you'll probably come across a statement that you don't know how to prove right away. The last two proofs I showed you, the last two proofs I wrote out, I've seen the proofs for them, I've done them before, so I knew how to prove them. So I could just start and finish, in a pretty organized way without doing any preliminary work. So one thing that's very often done is like, hey, now this is a universal statement about all positive real numbers, right? This is for any pair of positive real numbers. The sum of their reciprocals, the reciprocal pairs here, x divided by y plus y divided by x, will be greater than or equal to 2. Very often, when you have universal statements, you do some exploring. Explore. Do you believe that this is even true? Because you're not going to try to prove a statement that you don't believe is true. So the question is, do you believe it's true? So you start going through some examples to see if you believe it. Just take any pair of positive real numbers. Well, how about if x and y are both equal to 1? Well, then you would have 1 divided by 1 plus 1 divided by 1. That's equal to 2. And yeah, that's greater than or equal to 2. That's true, right? How about if x were 3 and y were 5? Right? Again, just picking any pair of real numbers, positive real numbers. Then 3 divided by 5 plus 5 divided by 3. If you put this together, get common denominators and all that. this would be 9/15 plus 25/15. 9 plus 25 is, this would be 34/15, and that's greater than 2, right? This is 2 and 4/15, so it's definitely greater than or equal to. That's true, right? I mean, I'm not going to do this for the rest of the video, right? I'm not going to make this too long, but you could do this all day long. Now it says any real numbers as well, not just integers, right? I picked some integers here, but I could have x be pi and y be the square root of 2, and then maybe use a calculator or something to show that x divided by y plus y divided by x is indeed greater than or equal to. And maybe I'll just do that for one more example. I'll pull a calculator up. All right, and then we so like I said, how about just I can use pi and square root of 2, any positive real number. So I do pi divided by the square root of 2, and then I add to this the square root of 2, and then divided by pi, and then hopefully again, if this is truly a true statement, this will be greater than or equal to 2. Look at that, it's 2.67. And again, you can do this all day long. Now that's not proving anything, right? Just I mentioned that in the section 2.3 on common mistakes. This is a universal statement. Just doing a few examples. I have done 3 examples now, 2 here and 1 on the calculator, and shown that this is true for 3 examples. But 3 examples is not enough. That's not everything. That's not every pair of positive real numbers. But it gives me a rough idea. It makes me feel like, yeah, I believe this is a true statement. All right. So you get some exploration, some brainstorming. Now, like, you think, how would I go about this? Maybe do some scratch work. All right, so again, this is preliminary work. This is not the proof. Then perhaps I do some scratch work. So in scratch work, you can start at the end, because this isn't the proof. So I write down that statement. X divided by y plus y divided by x is greater than or equal to 2. And I start messing with this. I start doing some algebra. And I figure, we know that x has to be positive, right? We're dealing with positive real numbers. Y has to be positive, right? So x and y are greater than 0. We know this. And let's mess around with this. And I mess with this until I get to a statement that I know is true, and then I kind of work backwards. All right. So if these are true, then we know that this is an algebra rule, right? Then x times y must be positive, right? This is just an algebraic rule. If I multiply the top one by y or the second one by x, I'd get x times y is positive. And then this is another algebra rule. I could take this inequality here, multiply both sides by xy. Right? We have x divided by y plus y divided by x greater than or equal to, and again, take this side here, 2, and multiply it by xy. And I can do that, right? X times y would be a positive real number. Multiplying both sides by xy won't change the inequality, right? The only way that the inequality will flip is if you multiply by a negative. And if I distribute xy over here, you'd get x squared plus y squared, right, because the y's and the x's would cancel, is greater than or equal to 2xy. Then I still don't see. I know that. Remember, there were some other rules. Remember something we know is true. Something you can assume is that when you square a real number, it's going to be positive, right, or non-negative. So I know that's a non-negative number. That's a non-negative number. But would this necessarily be greater than this? I don't know. So I keep messing with it. What if I were to subtract 2xy from both sides? Right? Just do some more algebra here. Then we have x squared minus 2xy plus y squared is greater than or equal to 0. Right? Very often the number 0 is important because we know a lot of things about negative numbers, non-negative numbers, that all deals with the number 0. When things are positive, they're greater than 0. When things are negative, they're less than 0. The number 0 is huge. So I like, maybe I'll like introducing 0 into my scratch work. And then something else algebraic. X squared minus 2xy plus y squared, this is factorable. this actually factors to x minus y squared, which is greater than or equal to 0. And here, this is perfect, right? This is perfect. If x and y are real, and one of those things you can assume is that that the real numbers are closed under addition and subtraction and multiplication, right? You take any two real numbers, it's just like the integers. Now you could also prove it, but we'll just use the assumption here. If you take two real numbers and add them, you get another real number. You take two real numbers and subtract them, you get another real number. We know that x and y are real. When we subtract them, it'll be real. And a real number squared being greater than or equal to 0, this is an assumption. Right? This is an assumption. This is something from the last section. Remember, when you take a number, a real number, and square it, you're going to get a non-negative result, something greater than or equal to 0. So this is where I'm going to stop my scratch work. I have come across something here that I can assume to be true. I have come across something that I know to be true. And then we kind of work our way backwards. All right, and I'll show you what I mean. Work backwards in the proof. All right, when I go to write the proof. So I did a bunch of a bunch of scratch work here, crap work, whatever you want to call it. All right, where I used some algebra, and I eventually got down to a statement that I know is true. And then I kind of work the steps backwards to the statement we're trying to show is true. Okay. And then I'm going to write this all out in words. So I've explored a bit. Right? I believe this is true. I worked with that statement. I work with the conclusion. And I don't know that this conclusion is true. Right? We're trying to show that that's true. I work with the conclusion until I see a statement that is true, and then I work backwards when I actually go to write the proof. All right. So all this stuff the reader will not see. Right? I am not going to show this to the reader, all the work I did. Then I write the proof. So now I'm covering up this preliminary work, right? Covering it all up. I'll keep it in mind, right? I'll have it off to the side. I have it off to the side for myself to read and use. And now I organize it into a valid proof. So proof, right? I indicate where the proof is starting. So remember, you have a hypothesis and conclusion. The hypothesis is x and y are positive real numbers. That is what we're going to start off assuming. So I'm going to let x and y be positive real numbers. Right? Introduce the variables, say what they are, and start off with the assumption from the hypothesis. We will show, right, and now I'm going to let the reader know where we're going to be going. We will show that x divided by y plus y divided by x is greater than or equal to 2. All right, I'm just telling the reader where I'm going to stop. All right, now going back to the assumption from the hypothesis, I start off again with x and y are positive real numbers. So by definition, what is it? What does it mean to be positive? Right? By the definition of a positive number, x must be greater than 0, and also y is a positive real number. Y must be greater than 0. Right. Now, since x and y are real, I am telling you they are real in this initial assumption. Since x and y are real, again, like with the integers, their sum will be real. Their difference will be real. Now, you could prove these statements, but again, in algebra class, right, basic algebra rules, you learned about the real numbers, right? Everything you did in algebra was dealing with real numbers. I mean, I know there were some things in other sections of algebra dealing with the complex, the imaginary numbers too, but most of the stuff you did in an algebra class, most of the algebraic rules you learned were involving the real numbers, and this was one of them. Since x and y are real, right, x minus y is also real. Again, you can prove this if you wish, but I don't want to take up too much space in the proof. This is something we can assume. Right. Now here's where I look at my scratch work. I'm going to start the next thing I write will be this. We know that x minus y is real, so its square must be non-negative. So x minus y is also real. And then since x minus y is real, its square must be non-negative. Meaning the following, that x minus y squared must be greater than or equal to 0. And now comes a line of algebra, right? All my algebraic reasoning, right? Where again, just kind of going through my scrap paper, I go through my scratch work and kind of working backwards here, right, to the statement that we're trying to show, to get to this conclusion. So do some algebra, then multiplying this out. This is x squared minus 2xy plus y squared must then be greater than or equal to 0. All right, again, just you don't have to really. This is legitimate algebra. You don't have to really explain that. Just write the next line. Just don't skip more than one step. Just write one step at a time. And then I can add 2xy to both sides, right? That doesn't change the inequality. So then this leads to x squared plus y squared must be greater than or equal to positive, 2xy. All right, now the next part is going to involve some reasoning, right? Because I'll do this again one step at a time. Next, I'm going to divide by x, which will not change the inequality, and it's because x is positive, right? So then the next line, if I divide everything by x, you have x plus y squared divided by x must be greater than or equal to 2y. And again, this is since, and again, I write some reasoning here because maybe it's not so obvious. Why didn't the inequality change? Since x is positive, right? Dividing by a positive doesn't change the inequality. And then I'll do the same thing with y. Divide every term by y, and we'll get our conclusion. All right. We'll get that statement that we were trying to show to the reader. And then finally, x divided by y plus, and then dividing this by y gets rid of one of the y's here. Y divided by x is greater than or equal to 2. And again, the reason this is valid from the previous line is because y is positive, right? Dividing by a positive number will not change the inequality. And that's it. That is what I tried to show. That is what I said to the reader I will show, starting with the fact that x and y are positive real numbers. So I am done with the proof. And you see again, all I did here was kind of go backwards from my scrap paper, right, from my scratch work. But yeah, that happens a lot in proofwriting. The proofs that you see in a textbook are not, the author didn't just spit them out like that. The author had to organize that and create a final draft for the reader. Very, very often, in the proof that you see is not the work the author did. The proof is the final draft. I keep saying that, right? And you're going to have to do that often as well, right? When you see a theorem and you don't know how to prove it, work with the statement, work with the conclusion, do some algebra, do some scrap work until you get to a statement that you know is true. And then you can work backwards and write the proof out working backwards. Right? So hopefully that all made sense, that this scratch work stuff. Right? And then again, they give you an example here. Watch the video. It's probably pretty similar to what I just showed you. And here's the proof right there. All right, they did a little differently than I did, but hey, same result. All right, now I'll leave this one to you, putting in the steps of this proof. If x is a real number and x minus, actually, you know what? I should probably do this myself, because you see there's two assumptions. Oh, I guess you've seen one with two assumptions. Here x and y are positive. So I'll leave this one to you. If x is a real number and basically x equals 3, x minus 3 equals 0. So you're assuming that x is 3. Right? All this statement here is basically going to lead you to x is 3. But you would start with this. Assume x is a real number and x minus 3 equals 0. Right? That's the hypothesis. And then say to the reader, we shall prove that x squared minus 2x minus 3 must also be equal to 0. That's again what you're trying to show. So I'd start with that as step 1. And again, I'll leave it to you to say what the next logical steps are. All right, so I got one more proof. This is, again, a pretty long one. Introduction to proofs here. A direct proof about rational numbers. So this is where you're going to use the definition of what it meant to be rational. So so I'll write this theorem here in the activity, and again, I'll go through and show you the proof. And then again, they show you assume hypothesis is true, do some steps until you derive the conclusion. All right, so go to some piece of paper for this as well. Okay, so here's the statement, the theorem. If R and S are rational numbers, and go back to section 2.1, look at the what it means, define rational numbers. Then R plus S, their sum, will also be rational. All right, now I've mentioned before, with integers, the sum of two integers you can assume is an integer. That's just something that you can assume. Even with real numbers, which is a bigger set than the rationals, you can assume that the sum of two real numbers is real. It's just, remember, the real numbers are broken up into rational and irrational numbers. It's those sets of numbers that are tricky, that you have to actually prove statements about. Because yeah, rational numbers are real, but is the sum of two rational numbers also, just because the sum of two real numbers is real doesn't mean that the sum of two rational numbers is rational. We'll see that that's true, but we're going to prove it using the definitions of rational numbers, okay? So now this time again, I know I said a lot of times you're going to do scratch work and, maybe do some explorations, take some rational numbers like a half and 2/3, add them together. Do you get another rational number? Yeah. Take 5/7 and 8/9 and add them together. Do you get another rational number? Yeah, right. So like, do you believe it? Maybe do some exploration and stuff. But once you've done enough, you're like, hey, I believe this is true, and you've organized your thoughts. Then you can write a proof afterwards, right? So I'm just going to start with the proof, though. This one I know how to do pretty quickly. So again, you start off with the hypothesis. I'm going to say let R and S be rational numbers. And then again, you don't have to do this, but I like to tell the reader where you're going. All right, we will show the conclusion. All right, we will show that R plus S, that their sum R plus S is also rational. All right. Again, that's not the end of the proof. It's just telling the reader where you're going. All right, and then using my assumptions from the hypothesis, that R and S are rational. What does that mean? Right? What does it mean for R and S to be rational? So this is going back to section 2.1, right? By definition, the definition of a rational number, R must be equal to, say, again, the ratio of two integers where the denominator is not 0. Let's say m divided by n, where m and n are integers, and n is not 0. There shouldn't put a period there. And, because I got one more thing to say, the same thing for s. Right, again, I introduced new letters. I told you what they meant, what they are, introduced them properly. And same thing for s. S equals, and again, just two new letters. How about x and y? X divided by y, where Again, what does it mean to be rational? X and Y are integers, and the denominator Y, right, is not 0. Okay, so by the definition of what does it mean to be rational, here's how I can express R and S. And then pretty similar to some proofs I showed you earlier in the video, I'm just going to plug these into R plus S and see if we can express R plus S in the same way. Right? If I'm trying to show that R plus S is rational, it means I want R plus S to be equal to an integer divided by some non-zero integer. Plugging R equals m over n and s equals x over y into the expression R plus S yields the following. So we start off with R plus S equals m divided by n plus x divided by y. And now I'm going through some algebraic steps. Right? Now I'm adding fractions here. Rules of algebra, you can't add fractions unless they have the same denominator. So this I'd multiply by y divided by y, and this I'd multiply by n over n. And we'd have m times y plus x times n over the common denominator of n times y. Right, and then now I have to make a few statements. I have expressed R plus S as a fraction, but are these integers? And yes, they would be, right? Remember, we can assume closure under multiplication and addition for integers, right? I'll say since m, n, x, and y are integers, right? We establish them as integers up here. M times y plus x times n and n times y, these are both integers. Right, so the numerator and denominator of this fraction I got for R plus S are both integers, right? Due to the closure. Additionally, I want to make sure that the denominator is not 0. All right, well, we stated earlier, n's not 0 and y's not 0, so then their product must not be 0 as well, right? Additionally, also, since n is not 0 and y is not 0, n times y is not going to be 0, right? So now I've shown that, I guess I should call these integers. Let's call this my plus x, and let's call that k, integers k, and let's call ny j. So k and j respectively. Right, introducing new integers, and I'm telling you they're integers right here. Right. So k is representing my plus xn, j is representing ny. Right. So that means that j is not 0, right? J is ny. Okay. Therefore, we have just shown that R plus S equals, my plus xn is my integer k. N times y is this integer j, right? So for integers kj with j not 0, right? I showed that j wasn't 0 in this line. By the definition of rational, R plus S is rational. And so by definition, R plus S, this sum of R and S, the sum of two rational numbers, is a rational number, which is what we were trying to show, right? That was the conclusion. Right, I put the little box there to indicate the end of the proof. Okay, so again, very tedious work sometimes, writing out full sentences. I think that was actually a bad sentence. I should have, whatever, but you're trying to write statements with fleshed out reasoning, right? Make sure everything's explained properly to someone. Assume the person reading has no idea what's going on and you're trying to explain it to them. Right? That's what I want. Okay. And again, they go through this, the animation. They have an animation where they go through that kind of a proof as well. Right? They use A, B, C, and D instead of in you know, whatever. Right? They use different letters than I did, but it's the same kind of proof. All right, here, I'll let you do this one. What would you start off assuming? What would be the first step in a proof of, the square of any rational number is also rational? This is also like, if I have a rational number, say r, then its square, r squared, would be also rational. You could write it as an if-then statement, and I'll let you fill in the steps there. All right, and then your challenge, and this is the last thing, your challenge is, just a few of them. Suppose the following theorem is proven using a direct proof. So the theorem is if x is a real number and x is less than 5, so you're assuming both of these things, then show that x squared minus 20x plus 75 would be greater than 0. So what would be assumed at the beginning of the proof? Well, again, just the hypothesis here, just these two things, that x is a real number and that x is less than 5. So this thing here, right? And then I check that, and that's it, if it was a direct proof. Pretty simple stuff, that. And let's see what the next one looks like. Yeah, and it's the same thing. Now, look at the question, though. What would be proven by the end of the proof? That's the conclusion, right? That x squared minus 24x plus 128 is greater than 0. That would be shown. So just pay attention to what's being asked. All right, then you have your additional exercises. Some of these are in your assignment 3 that I'm going to have you, that you need to upload to me in Canvas. The solutions are there if you'd like to look at them to check yourself, but please, please, please try to do these on your own first before you look at the solutions. All right, you're not going to learn anything. I keep saying this. You're not going to learn anything if you just copy the solutions down. All right. Try to write these proofs. Try to do these problems without looking at the solutions first. And I would also recommend that you try to do all the problems, even the ones I don't assign. And there are a lot here that I didn't assign. And if you have questions on those, let me know. All right. And also be careful with the solutions. It was mentioned earlier that, and you've even seen my proofs, the proof they have won't necessarily be exactly like the proof you're going to write. All right. But as long as you have the same kind of structure, you may not use the same letters, you may not use the same words, but as long as the structure is the same, you state where the proof starts, you state your assumptions. Every time a new variable is introduced, you let the reader know what it represents. You have your steps and your reasoning, your statements and reasons and true statements, and they all follow from one another. You write in full sentences, and then once you're at the conclusion, you end the proof with some sort of symbol to indicate to the reader that the proof is over. And don't state anything without proving it, unless you can, unless it's something basic that we've seen, like in the previous, in section 2.3, you've seen some things that you can assume to be true. Don't use results that haven't been proven yet, that are ones that are bigger statements that you should prove. Don't use what you prove, don't use the conclusion in your proof. Don't you should end with the conclusion. Don't use it in your proof. And don't prove a universal statement by just showing a few examples. That is not a proof. Right? And then and don't show me the scratch work either. All right? When they're asking you to prove something, the scrap work, all the preliminary work, the brainstorming, the exploring, that is aside stuff. That's stuff on the side. That's behind the scenes. I don't want to see that. The proof is the final draft, when you organize all your thoughts. That's what I want to see, the organized final draft. Okay, so that's it for section 2.4, this introduction to writing direct proofs. Hopefully this video was informative, and my examples showed you, what I'd be expecting you to write in a proof, especially in a direct proof. We start with the hypothesis, end with the conclusion. hopefully you can use this as a nice little guide for you when you work on this stuff on your own. Let me know if you have any questions, of course, and thank you very much for watching.